again for giving me this opportunity to share this work with you. So this work is presented in this year's ICML. It is a joint work with Michael and Adrian. And in this work, we try to investigate a fundamental problem in likelihood-free inference. Namely, is it necessary to learn summary statistics, especially given the recent very powerful neural network-based approaches. So let's begin. So the main message of this work is as follows. First, we show that in likelihood-free inference, summary statistics itself may be easier to learn than the posterior. And the second is that we show that to learn sufficient statistics, we can maximize mutual information in some projective spaces. And we say that this task is easier than doing inference itself. And the third discovery is that we identify some failure modes of this end-to-end inference methods, such as SMPEC and SNR. So putting all this together, we want to answer the question in this title a little bit by saying that maybe doing learning summary statistics may still have a market in LFI. Okay, so this is the main content of today's work. First, I will quickly go through some background on likelihood-free inference and summary statistics learning. Then I will introduce our new method, SQBit, style sufficient statistics, for learning summary statistics in likelihood-free inference. Then I will apply this method for inference in a diverse set of implicit statistics models, where we will also compare these end-to-end inference strategies. Okay, let's first look at some background about likelihood-free inference and summary statistics. So as everyone here knows, likelihood-free inference is a set of techniques for doing Bayesian inference in some complex statistical model where the likelihood is injectable, but we can still sample data from the model. So this is typically done by repeatedly sample data from the model, and then you can learn some statistical objects from this sample data. Some methods focus on learning this likelihood function, and some focus on learning this posterior. A very important component in likelihood inference is this summary statistics, which is a compressive representation of the data such that it almost contains all information about the posterior. So this means that if we do Bayesian inference based on this summary statistics, it will be almost the same as doing Bayesian inference based on the original data. Or equivalently, we can look at the problem from an information theoretic perspective. That is, we say this summary statistics may preserve the information about the posterior almost the same as the original data. So this information theoretic perspective is important for some of the contents later. So at this moment, there are already some methods for learning summary statistics. The first one is the very classic moment-based approach, which directly takes the predicted posterior mean as the summary statistics. I mean the JRSSB paper for this approach. The second approach is the recently developed Inference statistics approach, which try to maximize the mutual information between the learned summary statistics and the model parameter. So in the figure of right-hand side, there is a comparison between a conceptual comparison between these two methods. For example, this Inference approach is theoretically can theoretically attain better sufficiency because of the connection between sufficient statistics and the Inference principle. But the bad thing here is that actually mutual information is quite difficult to estimate, especially when there's just limited samples. On the other hand, this moment-based approach has better sample efficiency because in this approach, we just need to solve a simple regression problem. However, this approach generally does not yield sufficient statistics. Actually, we can show that the moment-based approach optimizes a lower bound of mutual information. So this means that it will always lose some information. So I would like to mention that there also exist many other external approaches for learning summary statistics. For example, those based on score matching principle, those based on feature information maximization, and also autoencoder. But this will not be the focus of this work. Okay. I would like to highlight that besides these approaches for learning summary statistics, there also is some method that does not rely on summary statistics. I will call these approaches end-to-end inference method. This includes sequential neural posterior estimate method, or SNPE, or the sequential neural ratio estimate method, or SNR. So in either these approaches, we learn the posterior or the ratio by some neural network. For example, in SNPE, we rely on a neural density estimator, and in this neural ratio estimate method, we rely on some neural estimator. In both methods, the input data can be directly fed to an encoder jointly trained with the neural posterior or the neural ratio estimator. So in that sense, there's no need to learn summary statistics because this encoder can serve as the summary statistics function. Okay, so given the existence of this very powerful end-to-end inference method, which has been proven quite effective, do we still need to learn summary statistics? It seems there's no point for doing so because we already have this end-to-end methods. So let's think about this question from another perspective, which is what's the principle for learning summary statistics? So below this are just my personal opinion. I think if we want to learn some summary statistics, it should satisfy two principles. The first is the learning of such summary statistics should be easier than doing inference itself. Otherwise, we will directly resort to end-to-end inference, right? The second is this summary statistics should still be approximately sufficient. Otherwise, it will not be useful for inference. So these two principles seems to contradict with each other, but I will show you that actually this is possible. Okay, so let's move to the next part about our new method for learning this approximate sufficient statistics, which satisfy the two principles I mentioned before. So remember that previously we mentioned about the connection between sufficient statistics and the Inference principle. And we would like to maximize this mutual information for finding summary statistics, but we say that maybe estimating mutual information was too difficult. Oh, sorry, maybe too difficult. Maybe too difficult. So we want to find some alternative method. So our solution is that we can learn this Inference representation without estimating mutual information explicitly. So we do this by divide and conquer strategy, where we decouple the original challenging high-dimensional mutual information estimation problem to a set of low-dimensional mutual information estimation problem. So the original problem may be very difficult, but we can somehow convert it to a set of easier to solve problem in low-dimensional spaces. So we say that this low-dimensional mutual information is as easy to learn as solving some two-dimensional classification or machine learning problem. You can see that this is really very easy, and I will show you how this is achieved later. Okay. Let's look at more detail of our method. Supposing that now we are trying to maximize the mutual information between the learned representation and the model parameter. So this learn representation or our summary statistics is computed by some encoder function here. And we want to maximize the mutual information between S and theta here. So we don't want to directly maximize the mutual information between these two because it may be too challenging. So we first do something to process this data, which is, okay, we randomly sample some projection direction, this phi, uniformly from the surface of a hypersphere. We then generate this sliced version of theta by multiplying with this, projecting this theta onto some low-dimensional spaces. So this will generate a set of one-dimensional random variable. So originally we have a high-dimensional random variable theta, but now we just have a set of low-dimensional random variable theta prime. And then we also do something similarly, but this time we don't use random projection, but use some second level encoder. So this one is the first level encoder. So this one is the second level encoder, where we map this already low dimensional summary statistics to even lower dimensional second level summary statistics. And we call this second level summary statistics as prime. So the third thing we do is we maximize the mutual information between every pair of this low dimensional random variable. This is all the secret in our method. And it shows that if each of this mutual information, this small mutual information is maximized for each of these pairs, then it is equivalent to maximize the original mutual information, meaning that we learn sufficient statistics. So this is the secret behind our method. So we have a theorem saying that, okay, if we maximize the quantity here, this will give us sufficient statistics. Let's look at more detail of this formula. So randomly sample slicing direction from the surface of a hypersphere, and then generating this will generate as many low dimensional mutual information objects, and then we can maximize the expectation of this quantity. And after you maximize it, you will discover that, okay, the learn as this summary statistics will be approximately the sufficient statistics of theta. And in practice, we employ an among the color approximation to this objective above. So we replace this expectation by the Monte Carlo approximation here. Okay. Now the question is, how do we estimate or quantify this mutual information? So we already say that we already avoid solving high dimensional mutual information estimation problem, and now we estimate in low dimensional space. But we still have the problem of how to estimate it. It may still not be so easy, so we instead try to use some more reliable estimator to mutual information, or let's say use some other proxies to mutual information. This is because we are interested in just finding the argument mass of mutual information here, rather than knowing its exact value. So we can consider some proxies to mutual information that may have better properties. So the first method is to interpret mutual information as a distributional discrepancy between the joint distribution and the products of marginal distribution. So we mark that mutual information is the KR between these two distributions, right? And then we can replace KR divergence by the Yanzhi-Shannon divergence here. And once we do so, estimating this JSD will be very similar to solving a classification problem where we classify samples from the joint distribution and the product marginal distribution. For those who are very familiar with GAN, this should be a very well-known result. So in this sense, learning this summary statistics becomes solving a classification problem in low-dimensional spaces. And the second method corresponds to interpreting mutual information as the statistical dependence matching. And with this viewpoint, we can replace mutual information with distance correlation on non-parametric statistical dependence matching. And the formula here looks quite complicated, but actually, all we are doing here is trying to solve a matched learning problem where the pairwise distance of this S prime, the second level summary statistics, you correlate it with theta prime, the projected model parameter. So in this regard, we will solve a matched learning problem rather than estimating the original mutual information. Let's have a quick recap of what we already talked about here. So originally, we have a high-dimensional inference problem where we try to estimate some high-dimensional density or ratios, which may be quite difficult even with the help of neural network. But here, we say that the learning of summary statistics may indeed be much easier because we just need to solve some classification problem or matched learning problem in low-dimensional spaces. This depends on the estimator or the proxy we use when trying to estimate mutual information there. So because the learning of summary statistics can be solved by a set of low-dimensional classification and matched learning problem, which may be easy, we say that the learning of summary statistics may be easier than doing inference itself. So that's the main point of this paper. I would like to draw some connection between our developed approach with some existing work. So here, above here, this is our slide sufficient statistics, which try to maximize the average of mutual information in the projected spaces. So this is actually closely connected to the moment approach and also the Inference approach. Let's look into the details. So consider here if each of these fine, remember that this slicing direction is from the surface of a unit sphere. So imagine that now we don't randomly sample from the surface of this unit sphere, but just use one-hot vectors for this fine. And we use exactly k vectors. So k is the dimensionality of this model parameter. Let's assume that we now just have k one-hot vectors for this fine. And you'll discover that if we have k one-hot vector with this fine, then the object inside here will becomes the object here. This may not be so obvious at the first glance, but if you decouple the sum here, because this MSE loss can be decomposed into the sum of several the MSE among different dimensions. So these two are connected with each other. So this moment approach can be seen as a degenerate case of our method where there are only K1-hot slices. And also our method is connected with the recent Inference approach. The connection is if the number of slices goes to infinity, then we will recover the goal of this approach. But this time we do not suffer from the difficult to estimate problem in high dimensional space because we just estimate mutual information in low dimensional space. This figure may better provide a comparison between this method, these three methods. Like the information approach is theoretically sufficient, but it is not sample efficient. The moment approach is very sample efficient, but may not yield sufficient statistics. Our method may be at a split point between these two, achieving a good balance between efficiency and sample efficiency. So we take the best from the two worlds. Okay, so when doing inference, we use sequential neural likelihood method, another very well-known method for likelihood inference. So everything is the same as the original sequential neural likelihood method, with the difference being that instead of directly doing inference, we will first learn summary statistics by our approach. Then we will execute SNL on top of the learned summary statistics. Okay, that's all about our method. Let's look at some experimental results regarding to some application to inference in several implicit statistic models. So these are some inference tasks we consider in this work. So we here consider 5 tasks. Some of them are very well known to us, including the multiple variate GNK problem and the Vickers model. And these different tasks cover the cases with different data type, like the GNK model. In the GNK model, there are the data there is IID. But in Vickers models and the OU process model, the data there is a time series. And also, they have ranging dimensionality from 2 dimensions cases to dimensions up to 12. So in all these cases, the true posterior is either known or can be approximated up to very high precision. So like for some of the tasks there, the posterior can be analytically given, and for some cases, we can approximate it either numerically or based on approximate Bayesian computation with non-sufficient statistics. So we have a very low dimensional sufficient statistics for the Ising model, which allow us to approximate the true posterior up to high precision using a huge number of simulations. So we perform comparison from 2 angles. The first one is we want to compare our method with other summary statistics approaches, namely the mentioned moment approach and the Inference approach. And on the other hand, we also want to compare our new inference method with some end-to-end inference algorithms. So we want to see that, okay, whether not performing end-to-end inference will be more beneficial compared to these end-to-end inference strategies. So here we compare to SMPEC and SNR, which can be seen as the state-of-the-art method or very widely used method for end-to-end inference. So first, let's look at the comparison to other summary statistics. So here, in all the cases here, we use SNL in inference. So these 2 blue guys are the baselines, namely the Inference approach and the moment approach. So the 2 red guys are our developed approaches. So the red one corresponds to the case where we estimate mutual information by the JSD proxy, and the purple one. The purple one corresponds to the JSD case, and the red one corresponds to the case where we estimate mutual information by the distance correlation proxy. You can see that. Oh, sorry, I need to explain what's the S-axis over there. So the S-axis is the simulation budget, aka the number of simulated samples. The Y-axis is the discrepancy between the true posterior and the learned posterior. So remember that we mentioned in the you mentioned here, we know the true posterior either analytically or up to a very high position. So we can directly compare our infer posterior and the true posterior. So you can see that among nearly all the cases, our approach outperforms the baselines, except for one case, which is the Bayesian linear regression cases, where the moment approach is particularly well. The reason for this is that actually for this task, the moment approach is the ground truth sufficient statistics, so it can perform much better than our developed approach. But for other cases, you can see that our approach is generally more preferable than this baseline approaches. So in this table, we compare our method with some end-to-end inference strategies. We also compare with the original SNL method. So our method here is SNL plus developed S-qubit method, just as mentioned before. So we see that, okay, again, our method is more preferable in most cases, especially in this Bayesian linear regression problem and this OU process problem, where the dimensionality is relatively high. And if we look at this Bayesian linear regression problem, where the dimensionality is so high, up to 12 dimensions, you will discover that these end-to-end inference strategies may not be so reliable, given the 10,000 simulations there. So the KR between the infer posterior and the true posterior is so large. So one possible explanation for this is that according to recent researches, ratio estimation method like SNR, SMPEC may be unreliable in high dimensional cases, where because in this case, the two distribution to compare are too distinct. So actually, we are already approaching the end of this talk. So here are some takeaways. The first is that we say summary statistics may indeed be easier to learn than posterior inference itself, because it can be done by solving a set of low-dimensional classification or machine learning problems. The second is we discovered that these end-to-end inference strategies can occasionally be less accurate in high-dimensional cases, like the Bayesian linear regression tasks there. And the third one is I would like to say that let us rethink a problem, which is what objects are easier to learn in likelihood-free inference. So maybe the likelihood itself is easier to learn, the posterior is easier to learn, or the ratio, the score, or the summary statistics. In this work, we show that maybe the learning of summary statistics is easier than other objects, but perhaps we may have a different answer later. So I think rethinking this problem will be very important for developing new likelihood-free inference algorithms. The last one is beyond the scope of likelihood-free inference. It is about general representation learning, where we show that, okay, to do informative representation learning, it can actually be done in low-dimensional projective spaces. So this may be much easier than directly solving the original informative problem. So yeah, that's the end of this talk. Thank you so much. I hope you enjoy.